Manganese deposits of India. Objectives. The objectives of learning this module are to understand importance and uses of manganese ores, mineralogy and textural features of manganese ores, genesis of manganese mineralization and its relation to crustal evolution. Manganese mineralization in space and time. World's distribution and Indian occurrences of manganese ores. Manganese nodules. Origin and future prospects. Distribution and geological features of manganese ores of India. Introduction. Manganese is the 12th most abundant element and is represented in nature by only one stable isotope, manganese 55. Manganese exists in +2, +3, and +4 valence states. Importance of manganese mineralization. Commercially exploitable deposits of manganese occur both on the continents and on the floors of the present-day marine and lacustrine basins. During the last 2 decades, emphasis on the study of manganese deposits has shifted considerably from those located on the land to the large accumulation on the floors of the present-day basins. The study of manganese nodules and crust on the floors of recent basins has not only shed new light on the resource potential but has also provided adequate opportunities to observe the process of formation of manganese deposits at any given time. The study of ocean floor deposits, in conjunction with the concept of plate movements, unravels the complete geochemical cycle of manganese. The metal is derived from the weathering of crustal rocks or volcanic exhalations and is deposited on the ocean floor. Consumed in subduction zones riding on the oceanic crust and is recycled to form new igneous rocks and associated ore bodies. Many manganese deposits now resting on the continents have been recognized as having originally formed the ocean floor, and thus a connecting bridge between the deposits on the continents and those occurring on ocean floors has been established. Manganese is the most important ferroalloy metal essentially employed in the manufacture of high manganese steels and also carbon steels. 95% of manganese is used for metallurgical purposes and minor amounts in the manufacture of alloy like bronze. Manganese is essential to iron and steel production by virtue of its sulfur-fixing, deoxidizing, and alloying properties. Among a variety of other uses, manganese is a key component of low-cost stainless steel formulations. Small amounts of manganese improve the workability of steel at high temperatures. In the iron and steel industry, manganese ore containing 28 to 35% manganese is used. Ore size generally varies from 10 to 40 mm. For manganese ore used in ferromanganese industry, besides manganese content, other important considerations are high manganese to iron ratio and a very low content of harmful phosphorus. Manganese alloy is the largest produced ferroalloy in the world with a share of about 41% of the global production of ferroalloys. Aluminium, with a manganese content of roughly 1.5%, has an increased resistance against corrosion. Uses. In the chemical industry, generally, high-grade material is used for potassium permanganate. Ore containing manganese oxide 80% minimum, silicon oxide 5% maximum, ferrous oxide 5% maximum, and 200 to 250 mesh ore size is used. Manganese sulfide is used in the manufacture of salts and in calico printing. Manganese chloride is used in cotton textile as a bronze dye. Manganese salts are used in photography and in leather and matchbox industries. Manganese dioxide is used for manufacturing dry cell batteries in which it functions as a depolarizer of hydrogen. Manganese dioxide has been used since antiquity to neutralize the greenish tinge in glass caused by trace amounts of iron contamination. Manganese is also used as a brown pigment that can be used to make paint and is a constituent of natural umber. Manganese compounds have been used as pigments and for the coloring of ceramics and glass. In the glass industry, ore analyzing manganese oxide 80%, preferably 86% minimum, ferrous oxide 5%, preferably 0.75% maximum, silicon oxide 2.8% maximum, aluminium oxide 1.1% maximum, barium oxide 1.3% maximum, calcium oxide 0.4% maximum, and magnesium oxide 0.4% maximum is preferred. Manganese also finds use as dryers for oils, varnishes, and paints. Manganese is an essential trace nutrient in all known forms of life. Manganese has no satisfactory substitute in its major applications. Mineralogy. Manganese bearing minerals occur as oxides, hydroxides, carbonates, silicates, and rarely as sulfides, arsenates, and phosphates. However, manganese deposits composed of oxide, hydroxide, and carbonate minerals of manganese constitute economic grade ore deposits. The various ore minerals of manganese are pyrolusite, silomelane, manganite, rhodochrosite, osmanite, jacobsite, cryptomelane, hollandite, ensutite, bronite, todorkite, lithophorite, rendenbergite, bixbite, rhodonite, birnasite. Textures exhibited by manganese ores. Manganese ores commonly exhibit the following textural features. Stalactitic, elongated forms of manganese minerals deposited from solutions by slowly dripping water. Banded, containing alternate bands of silicate mineral and manganese ore. Bedded ore, consisting of alternate layers of host rock and manganese ore. Stalactitic, banded, bedded. Poulitic, pisolitic, spherical grains of manganese minerals composed of concentric layers of diameter 0.25 to 2 mm are oolites. Rocks composed of concentric layers larger than 2 mm are pisolites. Cavity filling, growth of crystals on the walls of planar fractures in rocks, with the crystal growth generally occurring normal to the walls and cavities. Oolitic, pisolitic, cavity filling. Genesis of manganese mineralization. Genesis of manganese ore is believed to have occurred due to precipitation from hypothermal solutions, volcanogene sedimentary deposit, or by sedimentary processes, non-volcanogene sedimentary deposit. Volcanogene sedimentary deposit. Formation of manganese deposits of different geological ages from hydrothermal fluid has been suggested. This is supported by occurrence of many deposits at or near active seafloor spreading centers such as Mid-Atlantic, Mid-Indian, Pacific Antarctic ridges and seafloor bottom fracture zones. The seawater may act as a metasomatic fluid and substantial leaching of heavy metals by seawater, followed by their precipitation on re-emergence on the ocean floor has been visualized. Deposition of hydrothermal manganese and iron manganese oxides may either take place by direct precipitation from hypogene fluid forming hydrothermal deposits or through interaction of the hypogene fluid and the basinal waters, leading ultimately to hydrogenous precipitation. Non-volcanogene sedimentary deposit. The process of chemically controlled sedimentation is responsible for the formation of vast majority of the manganese deposits in recent and ancient geological sequences. The major sources of metals are identified as fluids derived from endogenous system, mainly submarine volcanism and circulation of water at considerable depth, and exogenous processes of weathering of pre-existing rocks, where endogenous systems provide the source and manganese deposits are ultimately formed by the process of sedimentation in a hydrodynamic regime. The term volcanogenic sedimentary is used. Such deposits exhibit characteristic sedimentary features and conformable interstratification. Genesis of manganese mineralization. For sedimentary deposits formed in a regime devoid of effects of volcanism and through derivation of metals from weathering zones situated either on the continents or on the seafloor, the term non-volcanogene sedimentary is applied. Studies in the present-day marine and lacustrine basins have clearly demonstrated that in most cases, no single source or mechanism by itself could give rise to manganese deposits. Many sedimentary manganese deposits were subsequently modified through metamorphism of different intensities. Frequently, metasedimentary manganese oxide ore bodies and manganese silicate rocks show an intimate and conformable relationship in a syngenetic sequence, although one may also occur in the absence of the other. Supergene concentration process at or near the surface in the weathering zones of mainly tropical countries was responsible for the formation of many large manganese deposits. Supergene concentration process involves leaching by surface and subsurface water, leading either to dissolution of elements other than manganese in the country rock or dissolution and reprecipitation of manganese in the near surface environment within the weathering crust. The solubility of manganese is far greater than that for iron or aluminium, and solubility of manganese is very effectively accelerated by simple organic decay and possible by bacterial reduction. Among the various genetic types of manganese ores, the largest accumulations of rich varieties occur in supergene settings associated with lateritic crusts. Manganese mineralization and crustal evolution. The various genetic types of manganese deposits now resting on the continents can be broadly correlated with the general pattern of the crustal evolution. In the early stage of basin volcanism, manganese ore bodies associated with greenstone and jasper predominated. With the development of the UGO synclines, manganese ore concentrations were formed in association with pyroclastics, volcanic rocks, basalt, andesite, dacite, and stratiform iron and base metal sulfide deposits on the seafloor. In more advanced stages of geosynclinal development, manganese deposits also formed substantially in the myo-geosynclinal domain. The most conspicuous development of manganese deposits in geological history, however, is found on platforms which are mostly devoid of volcanic rock association. The remarkable metallogenic province of Morocco contains, within a relatively small area, manganese deposits ranging in age from Precambrian to Myo-Pliocene. Manganese mineralization in space and time. Manganese deposits show a very wide range of distribution both in space and time. Manganese formation extends through the greater part of the geological history of Earth, and they are extensively distributed both on the continents and on the bottoms on the present-day ocean, shallow sea, and lakes. The deposits occurring on the land belong to geological formations of various ages ranging from early Precambrian to recent. However, concentration of manganese ores was not uniform at all ages, and major epochs of manganese deposition can be broadly identified. Manganese ore concentration was most extensive during Cenozoic, followed by the Precambrian, the Paleozoic, and Mesozoic in that order. In the present-day basins, evidence of deposition of manganese oxides has been found in sedimentary record since the Eocene, and the process continues even today. A variety of factors controlling the evolution of Earth, namely tectonic activity, volcanism, and climatic variations, have been invoked individually or jointly to explain the distribution of manganese ore deposits in space and time, but no unique model has been unambiguously recognized. World distribution and Indian occurrences. Only a small fraction of global manganese reserves is clearly economic. This fact continues to support interest in deep-sea manganese nodules, which constitute an enormous untapped resource. Most nodules are found in areas of deep-sea floor at water depths of 5 to 7 km. The Pacific Ocean alone is estimated to contain about 2.5 billion tons nodules containing about 25% manganese, making them similar in abundance to low-grade land-based deposits. World occurrence. More than 95% of global production of manganese today is from barely 7 countries, namely Commonwealth of Independent States, Republic of South Africa, Brazil, Gabon, Australia, China, and India. South Africa accounts for about 75% of the world's identified manganese resources. Most major steelmaking nations lack manganese resources. World distribution of important manganese deposits. Manganese deposits of India. India is one of the largest producers of manganese ore in the world. The distribution of manganese ore resources, production of manganese ore in India is given in the figure. Maharashtra 28%, Madhya Pradesh 27%, Odisha 23%, others 6%, Andhra Pradesh 14%, and Karnataka 6%. Manganese ore mining in the country is carried out by open cast as well as by underground methods. Manganese ore deposits of India can be classified into two major genetic types, viz. Volcanogene sedimentary and non-volcanogene sedimentary. Several of these deposits were also subjected to various degrees of supergene alteration, enrichment, partial dissolution, and redeposition. Manganese deposits of hydrothermal origin have not been reported from the Indian subcontinent. Manganese deposits of India range in age from late Archean 3000 million years to middle Proterozoic 900 million years and are distributed in the states of Jharkhand, Orissa, Andhra Pradesh, Karnataka, Rajasthan, Madhya Pradesh, Maharashtra, Goa, and Gujarat. World distribution and Indian occurrences. The manganese deposits of India are found in association with the following groups of Precambrian supracrustal rocks. Iron ore group 2950 to 3200 million years. Dharwar supergroup 2900 to 2600 million years. Kondalite group 2650 to 1600 million years. Aravalli supergroup 950 to 1500 million years. Chamnar supergroup 950 to 1500 million years. Sasar group 846 to 986 million years. Gangpur group 846 to 945 million years. Penganga beds 846 to 945 million years. Distribution of manganese ores in India is shown in this map. Manganese deposits associated with Precambrian iron ore group. Manganese deposits confined to the supracrustal rocks of iron ore group are encountered in the states of Jharkhand and Orissa. The manganese oxide ores are intimately associated with tufaceous shales and cherts of the iron ore group, and both stratiform and lateritoid type manganese ores are reported. Mineralogically, the stratiform manganese ores are composed of pyrolusite, cryptomelan, todorokite, and minor manganite and braunite. Lateritic manganese ores consist of pyrolusite, cryptomelan, with minor lithiophorite. Firma, an engineer, proposed a lateritic origin for the manganese ores of the region. Spencer suggested a hydrothermal origin, while Sen proposed a submarine volcanic origin. Prasad Rao and Murthy 1956 opined that the manganese solutions derived from weathering of syn-sedimentary manganiferous formations at a depth gave rise to manganese deposits. Subramaniam and Murthy 1975 and Banerjee 1977 favored a volcanic source for the manganese deposits. Roy 1981-1986 preferred a volcanogenic or pterogenous source for the stratiform manganese deposits of the region. Manganese deposits associated with Kondalite group. Stratiform manganese ores of the meta-sedimentary type hosted in the Precambrian Kondalite group occur extensively in the Srikakulam district of Andhra Pradesh and Koraput and Kalahandi districts of Odisha. The Kondalite group is composed of calc granulite, garnet sillimanite graphite granulite, garnetiferous quartzite, and quartzite. The manganese ore bodies are conformably interstratified with the various members of Kondalite group at different stratigraphic levels. The manganese ores and the associated rocks have been subjected to granulite facies metamorphism. Mineralogically, the metasedimentary manganese ore bodies are composed of braunite, hollandite, jacobsite, haussmannite, Friedenbergite, and the supergene minerals are represented by pyrolusite, cryptomelan, and minor ensutite. Roy 1960. Firma 1909 proposed that the manganese ores in the area are formed from the supergene alteration of codurites, a hybrid rock consisting of spessartine garnet, K. feldspar, and apatite. Sri Ramadas 1963, Rao 1963-1964, and Roy 1960-1966 opined that manganese ores are of metasedimentary origin which were later subjected to supergene alteration. Manganese deposits associated with Aravalli supergroup. Stratiform manganese ore deposits confined to the Precambrian Aravalli group occur in the Jhabua district of Madhya Pradesh and Udaipur district of Rajasthan. In Madhya Pradesh, manganese oxide ores are interstratified with gondite, quartzite, and phyllite. Mineralogically, the manganese ores are composed of braunite, bixbite, hollandite, and jacobsite. In Rajasthan, manganese oxide ores occur as conformable beds within carbonaceous phyllites and are associated with phosphorite and copper mineralization in the Matten Formation. Manganese minerals are represented mainly by pyrolusite and cryptomelane. Nayak 1966 opined that regional metamorphism of the manganiferous pelitic, semitic, and calcareous sediments resulted in the development of oxide and silicate ores of manganese. The metasedimentary manganese ores were later subjected to supergene alteration, giving rise to supergene manganese ores. Manganese deposits associated with the Champner group. Metasedimentary manganese oxide ores associated with the Champner group are reported from the Shivrajpur Bamankuwa area of Panchmahal district in Gujarat. Manganese ores in the area occur as bands interbedded and co-folded with cherty, quartzite, and phyllite. The ore-bearing sequences in the area have been metamorphosed to green schist facies, as evidenced by the presence of braunite and recrystallized pyrolusite. Gondite is totally absent. The manganese oxides are made of braunite, hollandite, bixbite, and hossamonite, and supergene alteration resulted in the formation of pyrolusite and cryptomelane. Manganese silicates include garnet, rhodonite, and manganese-bearing pyroxene. Supergene alteration of the metasedimentary manganese ores has yielded pyrolusite, cryptomelane, and manganite. To the east of the Shivrajpur Bamankuwa area in the Goldangri Hill, manganese oxide ores are interbanded with manganese silicate rocks enclosed in calc silicates. The metasedimentary manganese ores consists of braunite and hollandite with minor bixbite and hossamonite. Supergene alteration of the metasedimentary ores resulted in the development of pyrolusite and cryptomelane. Sen 1964, Roy 1967 proposed a contact metamorphic origin for the manganiferous rocks. Manganese deposits associated with saucer group. Manganese ores associated with the saucer group of rocks occur in Madhya Pradesh and Maharashtra, extending as an arcuate belt for a length of over 200 kilometers with an average width of about 30 kilometers. Metasedimentary oxide manganese ore bodies interbedded with metasediments of the saucer group comprising of pelitic, semitic, and carbonate rocks are encountered in Balaghat and Chindwara districts of Madhya Pradesh state and Nagpur and Bandara districts of Maharashtra state. Manganese ore bodies occur at the bottom, middle, and top of the argillaceous Mansar formation of the saucer group and also within the underlying calc-silicate and marble-bearing Lohangi formation of the saucer group. In the Mansar formation, interbedded manganese oxide ores and manganese oxide silicate rocks, gondites, exhibiting primary sedimentary structures forming syn-sedimentary sequences occur. The metasedimentary formations have been subjected to green schist to amphibolite facies metamorphism. Manganese minerals reported are braunite, hollandite, jacobsite, manganite and bixbite, spessartine and rhodonite. Manganiferous formations associated with the Gangpur group are encountered in the Sundargarh district of Odisha. The manganese oxide ore bodies and gondite are interbanded and co-folded with the pelitic schists of Goriojor formation, which constitutes the upper formation of the Gangpur group. The pelitic schists and the manganese ores have been subjected to amphibolite facies metamorphism. The manganese ore bodies are composed of braunite, bixbite, hollandite, jacobsite, hossamonite, friedenbergite. Manganese deposits associated with Penganga beds. In the Proterozoic Penganga beds that occur in the Godavari Rift Valley in parts of Andhra Pradesh and Maharashtra states, the manganese oxide ores are interstratified with stromatolitic limestone and intermixed with chert, jasper and shales. The manganese ore beds exhibit penny-contemporaneous deformation, pinch and swell and slump structures along with diagenetic features. Manganese is essentially composed of todorokite, pyrolusite, ramsdellite, ensutite, benazite and minor braunite. Roy 1981 visualized a terrigenous source for manganese in the Penganga beds was that followed by diagenetic remobilization of manganese and reconstitution, leading to the formation of economic-grade manganese deposits. Manganese deposits associated with Dharwar supergroup. Manganese ores confined to the Precambrian Dharwar supergroup of rocks occur in the north-northwest, south-southeast trending supracrustal belts and encountered in parts of Karnataka and Goa. In Karnataka, the manganese ores are encountered in North Kannada, Shimoga, Chitradurga and Sandur schist belts. Manganese deposits in the Karnataka craton are restricted to the Chitradurga group of rocks. Prominent deposits are encountered in the Sandur schist belt of the eastern block of Karnataka craton and Chitradurga, Shimoga and North Kannada belts of the western block of the Karnataka craton. The north-northwest, south-southeast trending Sandur schist belt is well known for its economic concentrations of iron and manganese and is one of the best examples of the Precambrian greenstone belts of the world containing iron and manganese mineralization. Manganese and iron ore deposits are confined respectively to Deogiri and Ramanmala formations. Iron and manganese bearing ornites consist of quartz, hematite, magnetite, pyrolusite, cryptomelan, lithiophyllite and minor bronite. Manikemba et al. 1995 reported derivation of iron and manganese of the Deogiri formation from volcanogene hydrothermal solutions. The manganese and iron-bearing formations were deposited in the shallow shelf region within the photic zone and above the wave base. The manganese and iron oxides present in the aurenites, argillites, cherts and carbonates were subjected to supergene enrichment, leading to mineable economic concentrations of manganese ore. North Kannada schist belt consists of greater than 2.6 billion years supracrustal consisting of metabasals overlain by continuous beds of metasedimentary rocks. The metasedimentary succession is represented by conglomerate, orthoquartzite, aurenite, stromatolitic limestone, dolomite, phyllite, argillite, manganiferous formation and banded iron formation, succeeded by a thick sequence of grey wax. The metasediments belong to the Chitradurga group. The late Archean manganiferous and iron formations occur along north to northwest trending discontinuous ridges. Manganese exhibit massive, finely laminated and banded textures and are composed essentially of pyrolusite cryptomelan. World distribution and Indian occurrences. The host rocks exhibit isoclinal folding and green schist facies. Manganese and iron formations were intensely laterized during the Neogen period. The manganiferous formation varies from massive layers and are lenticular bodies, several meters thick sandwiched between phylitic layers, to very thin banded layers interbedded with similar layers of either quartzite, metachert or siliceous phyllite. Krishna Rao et al. 1996 invoke a volcanic source for the late Archean manganiferous formation of the North Kannada region. Subsequent lateristic alteration caused extensive remobilization of manganese from the metasedimentary ores. Chitradurga schist belt is a linear belt of supracrustal rocks extending for about 350 kilometers. Manganese mineralization is encountered mainly in the Chitradurga and Chikkayanayakkanahalli areas in the Chitradurga schist belt. Manganese mineralization is confined to manganiferous chert and phyllite. The uniformity in the composition of the manganese-rich bands and the co-folded nature of the manganese bands indicate they are metasedimentary in origin. Manganese nodules. Increasing global population, demand for metals, and dwindling land resources has led to the search of an alternative source for the metals could be in the world oceans. Oceans are considered as a warehouse for minerals, amongst others, polymetallic ferromanganese nodules, figure 9, phosphorites, hydrothermal sulfides, placer deposits, and sand. Polymetallic nodules deposits exhibit a variety of shapes, figure 10, black earthy color with size ranging from 2 to 10 cm in diameter. Manganese nodules. Ferromanganese nodules. Figure 10. Shapes of polymetallic nodules. Manganese nodules. Nodules occur at depths of about 4 to 5 km in the deep oceans and grow at a rate of about 1 mm in 1 million years. In the Indian Ocean, nodules occur in different basins such as the Central Indian Ocean Wharton Basin, Crustal Basin, Madagascar Basin, Somali Basin, South Australian Basin, and Arabian Sea. Manganese nodules. Under the microscope, the cross section of a nodule, figure 11, shows alternative layers of iron, dark color, and manganese, light grey color. Manganese nodules. The prerequisite conditions to form the nodules are low sedimentation rate, availability of nucleus around which accretion of oxides takes place, oxidizing environment, bottom currents of low velocity. The average composition of nodules is given in Table 1. You can see in the Table 1 the average chemical composition of polymetallic nodules. Manganese nodules. There are three processes for the formation of nodules. Hydrogenous process, whereby metals are supplied from the water column and these accrete on a suitable nuclei. Hydrogenous nodules have smooth surface texture and are rich in iron, cobalt, titanium, phosphorus, and lead content. The manganese-iron ratio of these nodules is approximately 1. Digenetic process supplies metals from the underlying sediment through the pore water by remobilization. Diagenetic nodules have rough surface texture and are rich in manganese, copper, nickel, and zinc content. The manganese-iron ratio is more than 2.5. Mixed type, which is a combination of hydrogenous and diagenetic types. Future outlook. Production of crude steel is the single most important factor in the demand for the manganese ore. Steel industry accounts for approximately 90% of world demand for manganese. Carbon steel is the principal market, accounting for 65% to 70% manganese consumption. Summary and conclusions. Commercially exploitable deposits of manganese occur both on the continents and on the floors of the present-day marine and lacustrine basins. The study of manganese nodules and crust on the floors of recent basins has not only shed new light on the resource potential but has also provided adequate opportunities to observe the process of formation of manganese deposits at any given time. Manganese has no satisfactory substitute in its major applications. Manganese deposits composed of oxide, hydroxide, and carbonate minerals of manganese constitute economic grade ore deposits. Genesis of manganese ore is believed to have occurred due to precipitation from hydrothermal solutions, volcanogene sedimentary deposit, or by sedimentary processes, non-volcanogene sedimentary deposit. Supergene concentration process at or near the surface in the weathering zones of mainly tropical countries was responsible for the formation of many large manganese deposits. The largest accumulations of rich varieties occur in supergene settings associated with the lateritic crusts. The various genetic types of manganese deposits now resting on the continents can be broadly correlated with the general pattern of the crustal evolution. Manganese deposits show a very wide range of distribution both in space and time. Manganese nodules constitute an enormous untapped resource in future. Summary and conclusions. Manganese deposits of India range in age from late Archean 3000 million years to middle Proterozoic 900 million years. The manganese deposits of India are found in association with groups of Precambrian supracrustal rocks. Increasing global population, demand for metals, and dwindling land resources has led to the search of an alternative source for the metals could be in the world oceans. Manganese nodules.